All right, I will now talk about the Plancherel formula in the context of finite groups. Already for finite abelian groups, we have proved that. Now, as we have been doing since the last video, we have been extending the theory of Fourier analysis on finite abelian groups to the general groups as far as possible. So we define the Fourier transformation in the context of general finite groups, and then we prove Fourier inversion. Now we will be dealing with the Plancherel formula. So let G be as usual. We retain the notation from our usual notation. So let G be a finite group, not necessarily this is abelian. And we also write Wi rho I, where I runs from 1 up to k, are all the uh, irreducible complex representations of G. And let's denote the dimension of Wi by Ni, and also for simplicity in notation and convenience, let's write the character of the irreducible representation rho I by chi I. So for all I. All right. Now, without any loss in generality, we can assume each rho I is unitary. So again, let me remind you what it means. What this means is for every G in G, the linear operator rho I G, which is operator from Wi to Wi, is a unitary operator. So provided what we mean when we say this is unitary, that means already there is an inner product on W such that with respect to this inner product, this operator rho ig for every G is unitary. In fact, this is not a serious condition at all, because already we have seen in one of the earlier lectures that whenever we are having a finite dimensional representation over C of a finite group, then indeed we can put an inner product on the space which makes each and every linear operator a rho. I mean, if the representation is denoted by rho, then we can make every linear operator rho G on the vector space unitary, right? So we will be now using that, because since we can do it for any representation, so it is not at all anything serious that if we throughout assume that the representation that we are considering are unitary. So, well, in our earlier results, that was not necessary. Therefore, we did not assume, but now we really need to assume, because once we assume the representation is unitary, then the Plancherel formula in this case, that will look better. Of course, without using that, you can formulate the Plancherel theorem, but somehow that looks more formal and more general, so that one can, for one, it becomes really difficult to convince himself or herself why that should be regarded as the Plancherel formula. Well, for finite abelian groups, we did not need that, because there any character means automatically the map goes inside S1. So that's already unitary. But here we need that. Again, let me tell you that, of course, without using this inner product unitary thing, you can formulate, but then that looks more general, and hence that looks more general. So it is, and the formulation is such that, like, if you want to see, you can look at what is given in Sarah's book. So without getting into this, you can formulate, but then from that formulation, it will be, it is not quite easy to convince it's not very easy to convince our own selves why that formula should be regarded as the Plancherel formula. Okay, So now since we have assumed unitary, so there must be some reason. So what's the advantage of working with unitary operators? This is precisely when we want to consider its dual. So recall that V is a complex vector space over V is a complex vector space, and A is a linear operator. Assume further that V has an inner product. V has an inner product over V has an Hermitian inner product. So what I mean by an Hermitian inner product is that it's a function which is linear in the first variable and semi-linear in the second variable. What it means is for each v lambda w, it will be lambda conjugate v w. And for addition, that it is the same. V comma w1 plus w2 is v comma w1 plus v comma w2. All right. So by an Hermitian inner product, we mean inner product over C that satisfies this property that it's linear in the first coordinate, first variable, and semi-linear, or some people call it conjugate linear, in the second variable. All right. And once there is an inner product, then we say an operator from V to V is unitary if that's for every V and W, inner product of AV and AW is same as inner product of V and W. All right. So now we assume that so A is a linear map from V is a linear operator on V, and V has a complex inner V has a Hermitian inner product on that. V is equal to the Hermitian inner product, and also we assume that dimension of V is indeed finite. Then there is a well-known theorem that is I presume that that's all that is contained that is discussed in any first course in linear algebra, which is known as the Riesz representation theorem. So the Riesz representation theorem says given any given any linear operator from V to V, so sorry, I just make a change. So consider a linear functional on from V to C. So the Riesz representation theorem says there must be a vector V in V such that AZ must be Z inner product V for every Z in V. So Riesz representation theorem says the structure of a linear functional when we on an inner finite on a finite dimension inner product space. So for example, let's repeat once again. So for any z maps to the, so first we fix a vector v, then for any z maps to the inner product of z and v. That's easily seen to be a linear functional from V to C, right? So once that is there, so now the Riesz representation theorem says, I mean, any linear functional on V has to be of this form. So therefore, there is no linear functional on V which is not obtained by the inner product by some vector V. Okay. So therefore, in view of that, now we know that there is a bijective map a priori from V to V star. So what this says is each V is being mapped to the TV. So what TV is? TV is the map from V to C. This is the TV is the linear functional corresponding to V. How is that obtained? That TV of Z is the inner product of Z and V. So TVZ is inner product of Z and V. So in view of the Riesz representation theorem, we have a bijection from V to V star that and that by which is given by sending each V to the corresponding linear functional TV. Okay. So then what is the scenario? So the scenario now becomes the following, that from V to V in one, so we have from V to V star. So I will shortly see the reason for drawing this diagram. So what we are going to do is the following, that recall that when if A is a linear map from V to V, then A star is the linear map from V star to V star, right? So A star is the linear map from, suppose we start with a linear map A, then A star is the linear map from V star to V star. How is A star defined? So any element F in V star that is being sent to so here A, so AF compose AF compose A. That is how the dual map of a linear map is defined. So this is the general, this is the general scenario. But when we have that V is of finite dimension, and furthermore V has an inner Hermitian inner product on that, then this takes a nice form, because then we know that every F is of the form TV for some V. So therefore A star of TV is nothing but TV compose A. And how does TV compose A go? So TV compose A being applied on Z. So this is precisely, so TV compose A is, by according to our definition, A star of TV compose A. So TV compose A is being defined as TV, so this will be TV of AZ, and again by definition this will be AZ in our product V. Okay, so the map, so given A, so the A star map sends each TV to the following map Z. Z is being mapped to AZ in our product V. That's what we have seen. So let's put that in the diagram. So for each V is being mapped to TV. So then, so A star of TV is the map given by Z is being mapped to the inner product of AZ and V. Now again, this is according, so A star of TV is in V star. So again, we use Riesz representation theorem. So this linear map must be of the form Z times some vector, right, for every Z. Because this is what the Riesz representation theorem says, every linear functional must be of the form. So for any given A, the vector for which for every Z this equals to this, we, for the time being, let us write that vector by A star V. Please note that A star V is just a notation right now. Don't confuse that with the image of V under A star, because A star is not, so far A star is a map from V star to V star, so A star V does not make any sense. So if A star V does not make any sense, if you regard A star V as the image of V under the map A star, that because A star is a map from as an operator on V star to V star. All right, but shortly we will see indeed that we can regard A star as a linear operator on V. So let's see that. So according to our definition, for every Z in V, so the inner product of AZ V is nothing but Z, the inner product of Z A star V. This is all Z and all V. That's what we have seen. Okay, because for each V we get TV, A star TV is a map, and that map by Riesz representation theorem there should be a vector. That's what we are defining. That's what we are defining by A star V. All right. So then what is what advantage that gives us? So that gives, so what the advantage that gives us is that we first observe that So again, our question is again the question that we want to ask here, that in this situation, what advantage does that give? So I mean, this using this Riesz representation theorem, so that the advantage that it gives is the following: that for any v, this a star v, if we send each v to an a star v, then that becomes a linear map. That becomes a linear map. Okay. I leave this checking to you. So recall that what we have done. So when we to begin with, A star was the map at the level of duals. So for each V, I have TV, and all elements in V star are like TVs. Then A star TV is again in V star. So we use Riesz representation theorem once again, so that then we get a vector which we denote by A star V, such that for every Z, the inner product of Z and A star V is basically the inner product of AZ and V. All right, fine. So that's how this A star V is defined. So again, as I said, that don't till now you should not confuse that confuse that with something as the image of the vector V under the map A star. That doesn't make sense yet. But shortly we will see that will make sense once we will do something. So in the first step towards that, first we observe that V goes to A star V is a linear map. Let me just check one step for you. I leave the entire everything. I leave the rest to you. So what is V? A star of V1, A star of V plus W. So according to the definition, A star of V plus W must be AZ times V plus W, right? According to the definition. And now you see this is AZ V plus AZ W, and that is nothing but saying that Z star V plus Z star W. So again, then we see that for each Z, so Z star V plus S star W is same as this. So therefore, A star of V plus W is S star V plus S star W. So the other, so the scalar multiplication, showing that A star preserves the scalar multiplication, that also can be proved in the similar way. Hence, I left that to you. So therefore, V goes to S star V is now a linear map. So once that we establish, so then in this context, when we do have an Hermitian in our product, here we make the following simplification. So since we have seen this, that from V star to V star, so in view of this, A star, so here it will be A star of TV, and that is nothing but T of A star V. In view of this, so in view of this, so exactly the diagram does not commute, but yeah, so this is what we have. So in view of this, what we will do now is we shall regard A star in that as a map from V to V itself. Again, let me tell you, in general, when there is no inner product, A star is a map at the level of dual. But when we do have inner product, then we can regard A star as a map from V to V itself. And in this case, we'll simply forget about the dual map, because as we have just seen, the dual map here now can be regarded as a map from A to V itself, because all that you need is what happens to this vector. Like if you have a map here, so that map has to be of the form TV. So all that you need, that what has to be with this vector, because this vector determines the map. So this vector determines that what is going to be the image of TV. since and so in view of that, it is quite natural to now to regard when A star is a map from V to V itself again, provided we do have an inner product. Okay, so once we have that it's an inner product, so now for the rest, whenever we have an inner product, we shall simply forget about the dual map, forget about the map at the level of dual, and I will always regard A star is a map from V to V. So I'm repeating that several times just to uh, I am repeating this again and again so that you focus on that, that from now on, whenever we will have in our product, then we are not going to bother about the map at the level of dual. All right, so again, let me just write for you. So the definition of A star is the following: AZV is Z A star V for every Z and V. Okay, so now let's come to the context of when we do now let's come to the context of representations. Okay, so if now so let's assume that our group is G and these are the irreducible these are all inequivalent irreducible representations of G. Recall that the Fourier transform sending each f to a f hat rho 1 and then f hat rho k. So this is a map from the group algebra LG to the direct sum of endomorphisms algebras. So this was our uh, Fourier transform. So now we will write the Plancherel formula. Plancherel formula is about inner product. So what we do is, suppose we have two functions phi and psi in LG. So then for phi, I have the tuple phi rho hat, and then phi hat rho k, and for psi I have similar thing, psi hat rho 1 and then psi hat rho k. uh, so these are the tuples in this direct sum of endomorphism algebras. So the Plancherel theorem will now talk about inner products. Plancherel theorem now will now talk about inner products. Well, what I mean is the Plancherel theorem, Plancherel formula will now show how to get the inner product from the inner product of phi and psi from the Fourier transform. Fourier transform of the maps. So the formula says that phi rho I. So the formula says the following, that phi rho I compose psi tilde rho I and star. So this is a linear operator on W from on Wi. We shall consider its trace, get it multiplied by Ni, which is the dimension of Wi. Then we just simply take its sum from 1 up to k and scale it by order of G square, and that is going to be the inner product of phi and psi. So this is the Plancherel formula in the setup of finite abelian groups. Okay, so we shall now prove that formula. So if you closely look at both the sides, you see both the sides are linear in the variables phi and psi, right? So because here it is just composition. Well, one more thing I should have mentioned earlier, which is also very easy to see, that suppose you have two maps A and B, A plus B star is same as A star plus B star. That is also very easy to see, hence I'm leaving that to you. So in view of this, so you see that both the sides are indeed linear in both phi and psi. So in view of that, so if we wish to prove the formula, it is enough to prove the formula when phi and psi are the basis elements. So we will now prove the formula when if phi is Ex and psi is precisely ui. Okay, so when this is ex and ey, so what is going to what happens to this to the inner product? So what is inner products of ex and ey? This is just 1 by g, 1 by order of g. Then a typical sum will come. So you see the sum is 1 if x equals to y, otherwise it is 0. So in this case, the inner product of phi and psi becomes the following, that if x equals to y, then this is 1 by order of g, 0 otherwise. All right. So now we will show that the left hand side also becomes this when phi equal to ex and psi equal to ui. Okay. So the first observation is what is ex apply, what is ex hat of rho I. Okay. So according to the definition, it will be summation exg rho I g, and unless g is x, the terms cannot survive. So this is precisely rho I x, right? Okay. Similarly, what is this? So psi, so ey hat of rho I is precisely rho I of y. Okay. Now we have its conjugate, rho I of. Now we have this rho I star. So what is rho I star? We have assumed that all rho g's are unitary, rho I g's are unitary. So therefore that immediately shows that then it has to, so when for an unitary operator a star is the inverse of a, right? So therefore rho I y star is nothing but rho I y inverse, which is again from the homomorphism property of rho I, simply rho I y inverse. So therefore their product is going to be the following. Therefore once you take that product, it will inside this, so this is simply rho I x y inverse, right? So this is this, and once you take their trace, it will be just chi I of x y inverse. So now this part becomes this. So the left hand side is precisely sum like this. The left hand side is precisely sum like this, and that is now divided by the factor. All right, you should not get confused by this when I underline that. That shouldn't be regarded as a I really am taking some conjugation. So yeah, so now again we know that how to compute such a sum. So this sum becomes, well, maybe I should yeah, so this sum becomes exactly equals to, so this sum becomes exactly equal to, so this sum becomes exactly equal to mod order of g if x y inverse is identity, that means x equals to y and otherwise 0. So this is what happens to the sum. And now since we have a factor outside, so this is what will happen to this. So this is what is going to happen with this. That is, this becomes 1 by order of g if x equals to y, 0 otherwise. Now you can see that for phi equal to ex and ey, psi equal to ui, both the sides match. So this formula holds when for any two basis elements ex and ey. Now the rest is just since we have since I mean both the sides, they have linearity. Well, to strictly speaking, there is a linearity in the first variable and there's a semi-linearity or conjugate linearity in the second variable here, and that's also here because this star part takes care of that, and hence we have the Plancherel formula for any phi and psi. So I'll just simply summarize what we have done. We have started with a finite group whose all representations are there, and we assume that all of them are unitary, and that's not a serious assumption. Then for an inner product, then we reviewed some basic stuff that shows that whenever we are working in a finite dimensional complex inner product space, then we can regard the dual map as a map from V to V itself, which is defined like this. And next, so this is a very general thing for this is a very general linear algebra observation in linear algebra. Now we come to the formula. So the formula says that how to get the inner product of two functions LG, phi and psi in terms of their Fourier transform. So this is what the formula is. And in order to prove the formula from the linearity in the first variable and the conjugate linearity or semi-linearity in other words in the second variable, it boils down to prove the formula for the basis elements. That's what we have done. And in view of that, the proof is now over. So I will stop now.